Collaborative robots must simultaneously be safe enough to operate in close proximity to human workers, while also being powerful enough to assist in industrial tasks such as lifting heavy equipment. These two design requirements are often at odds because the requirement for safety necessitates the robot be designed with low-powered actuators, while the requirement for performance often necessitates high-powered actuators. One way of navigating this performance-safety trade-off is through the use of static balancing mechanisms to offset the robot's self-weight from the actuators, thus enabling the selection of low-powered actuators without unacceptably compromising the robot's performance. In this paper, we present the design of a novel 2-degree of freedom wire-wrapped cam mechanism for static balancing. This mechanism consists of two cams that contact idler pulleys that are mounted on prismatic joints. These joints are connected to springs that connect to wires that wrap around the idlers and terminate on the end of the cams. A spring is placed between the two prismatic joints that pushes the idlers against the cams. This makes the torque on each cam a function of both cam angles. The profile of these cams are represented in polar coordinates with a polynomial modal basis. The shape of the cams are designed using an optimization-based approach. The optimization routine selects the cam shape modal coefficients and spring pre-extensions that minimize the following objective function. The first term in the objective function corresponds to minimizing the difference between the actual and desired cam torques. The second and third terms of the objective function correspond to minimizing the sensitivity of the output torques to unmodeled changes in spring stiffness. This optimization problem is subject to the constraints that both cams stay convex, the cams stay within a manageable size, and the maximum spring extensions are not violated. Other cam design methods that have been presented in the literature suffer from high sensitivity to unmodeled changes in spring constant, can return non-convex cams, and do not guarantee that the springs stay below their extension limits. Additionally, previous works on wire-wrapped cams assume the torque on the cams results from 2-point forces, one from the idler cam contact, that's normal to the cam, and one from the spring labeled spring 3 in this diagram, that's tangent to the cam. In this work, we relax this assumption and model the torque on the cam as resulting from a distributed force from the wire cam contact and a corresponding distributed friction force. Additionally, there is a force at the wire termination point. To test if these effects are significant, we built a prototype of this mechanism. In this prototype, two heavy X816 actuators are connected to 3D printed cams. Linear guide rails are installed for the prismatic joints. The deflection in the series elastic elements of the heavy actuators are used to estimate the torque on the cams. The prismatic joints are connected to off-the-shelf McMaster car springs. This video shows a sped-up version of the experiments. In these experiments, cam 1 is held fixed, while cam 2 sweeps from 0 to 90 degrees by 0.02 radian increments. Cam 1 then increments by 0.02 radians, and cam 2 sweeps back from 90 degrees to 0 degrees. This is repeated until cam 1 is at 90 degrees. At each angle, 20 torque measurements are taken. The results of this experiment are shown here. These results show that our model accurately predicts the torque on the cams to within 0.35 Newton meters. Additionally, it can be seen that the effects of wire cam friction can be significant for non-circular cams such as cam 1. Cam 2 was much closer to circular, and thus the difference between the infinite and finite friction models are more similar. Thank you for watching, and thank you to the National Science Foundation and Vanderbilt University for providing funding for this project.